I hope everyone's doing well. I'm Mr. Rich. Thank you for joining me. We're looking here at this function f of x is equal to a over b plus cx squared, where a, b, and c are constants. This function shows up enough in calculus that you should be very familiar with it, and an excellent shortcut exists regarding this function related to area calculations, that is integral calculus. Look, we have constants a, b, and c. If I were to make x equals 0, you know you'll have here a over b. That would be your y-intercept. You're looking at a 0 comma a over b pop out. If I were to do limit as x approaches positive infinity and I run the same function as you see, you'll end up seeing here a over infinity, which will be a 0 tending towards 0. If I were to say limit as x approaches minus infinity, the same function f of x, again the square converts the minus into positive and you're still looking at a over infinity. You're looking here tending towards 0. And the other thing is, if you look here at this function, it's equal to f of minus x. If you run minus x over here, you're looking at a over b plus c minus x whole square, which is equal to the original function. It tells you it's an even function, symmetric around the y-axis. When you bring this fact, and you bring in this fact, that fact, and this fact, it can help you easily graph these type of functions, and they all have a similar appearance no matter what a, b, and c is. You will remember that the y-intercept will depend on a and b. This right here will affect your y-intercept. So let's bring in these. Limit as x approaches infinity, we're tending towards 0. At minus infinity, we're tending towards 0. It's an even function. We now know what the y-intercept is. It's always a or b. These type of functions, if you graph them out, you'll always have a y-intercept here, 0 comma a or b. And then you will tend towards in 0 as you're going towards infinity, and likewise here it's even function, symmetric around the y-axis. The degree by which this function will drop, the curve will drop from the y-intercept, will depend on the constants as you see. But this right here is the basic form of these type. The very simplest form is 1 over 1 plus x squared, where you know the y-intercept will be 0 comma 1, and they'll still look the same. At 0 comma 1 right here, you'll still drop down on either side towards 0, a horizontal asymptote. If you were to look at these in regards to minus infinity to infinity, the area below curve calculations, these type of functions always have a finite convergent value. What is that value? This right here is a good shortcut for you all to remember. The area of these type of curves, when you're looking at from minus to infinity will always be equal to this. You see this a, you'll have a pi. The pi will come out from the arctan antiderivative divided by root b root c. If these b and c values can be simplified further because you have roots coming out, you can. Imagine if b was equal to 9, then you're doing root 9. You can obviously convert that into a 3. That's what I mean. Those values a, root b, and root c can be further simplified based on what the value is. But this right here will always be your form of your area below the curve. When you're doing minus infinity to infinity for these type of functions, the area calculation, a pi divided by root b root c, that's your template for your actual area answer. Now let's show you that in effect. That's our function. We've established it's an even function. We've established that the y-intercept is a or b. We also know towards infinity, minus infinity, it approaches the horizontal asymptote, your x-axis, meaning it approaches a value of 0 on either sides. If you were to look at this, you want to do the integral of this, how would we do it? And you are looking here from minus infinity to infinity, and we're doing now an area calculation, and I'm telling you that the area of this area below the curve will always be what? It'll be a pi over root b root c. You can bring these under a common radical if you want, but I'm just keeping them separate. But this right here is the outcome. How do you bring it about? You want to look here at the denominator b plus cx squared. You want to convert it into 1 plus u squared, because when you're looking at something which looks like this, you can bring out the arctan antiderivative, and that's what we want to do, bring out the arctan, and you can do it by means of a substitution. I'll do a substitution for x. If x were equal to, let's say, root b over root cu, then I know dx is equal to root b over root c du. And if you bring in the value infinity and minus infinity in places of this, it wouldn't make any difference. It would still be minus infinity and infinity, and we won't affect the limits. They'll still stay as is. When you bring in the substitutions, you can push the a out because it's a constant. Your limits can still stay as minus infinity to infinity. Then you bring in these items. You know dx is equal to this. Well, I'll have here a root b divided by a root c. Then I'll have here a du, as you see, all over b plus c. and I'll bring in the item for x. X is equal to root b over root c u, but I know it's a square because I have a square over here. When you clean this out, you have a root b over root c. I have an integral du over, let's look over here. I'm looking at a b plus c times b u square over c. These cancel out. I have here b plus b u square. I can isolate. When I isolate, I'm looking at b plus 1 u square. I can push the b outside the integral as a constant because it is, and I'm looking at 1 plus u square. After pushing the b out, I'm looking here at just that, and you see it, the arctan antiderivative has come out. I'm looking at that 1 over 1 plus u square because I'm seeing a 1 over here. 1 over 1 plus u square, the constants are outside. And this will bring my arctan antiderivative. But before we do anything, look at this. You can cancel out the root b and you can make this. I'm looking here at a over root b root c, but I'll clean it out and I'll write it again. I have brought out the constants a over root b root c, which is what I showed you right over here. A over root b over root c, the pi will come from the arctan antiderivative. When I do this, take it to completion, I'm looking at a over root b root c. The antiderivative here is arctan. I have here arctan u. You don't need to resubstitute. You know our limits are minus infinity to infinity. You'll have infinity minus infinity, and you can easily solve this out. How do you solve it out? Well, look at the graph of the arctan and go from there. When you look at the graph of the arctan, it's very easy, and it's this. You have the horizontal asymptote y equals pi over 2 and lower minus pi over 2, and your arctan looks something like this. As x approaches infinity, it approaches the upper horizontal asymptote, positive pi over 2. As x approaches minus infinity, you're approaching the lower asymptote, minus pi over 2. And then you're running those in. You have over here a pi over 2 minus pi over 2. When you compute this, you're looking here at a pi. And that's where that pi came from. When you take this to completion, you have your end result. Your end result is always going to be your area below the curve for a minus infinity to infinity improper integral a over root b root c pi. And that will represent the area, and it's right. Supposedly you were to be given a question. Let me give you a question and let's run it through using our shortcut, and it will be indeed correct. It would be sensible here to run through very quick examples using our template we see. This type of integral, improper integral minus infinity to infinity, will always have that area below curve calculation. If I'm looking at a question which is this, from minus infinity to infinity, we are looking at 11, let's say dx over 3 plus 7x squared. When I'm looking at this, I know my y-intercept is just based on a and b. The y-intercept will be 0, 11 over 3. It'll have all the other characteristics I've already talked about. Here's my y-intercept 0, 11 over 3, and it'll look like this. Then we're doing here this area calculation. It will be a finite value, and that finite value will be based on that template you see over there. When I'm looking at this area calculation, I know my a is equal to 11, b is equal to 3, and then c is equal to 7. My end result of the area below the curve, minus infinity to infinity, will be 11, the pi coming from the arctan, divided by root 3 root 7. This right here will be my area, and it will be correct. You can easily combine this to root 21 if you want. I'm just keeping it separate just so you see the various items a, b, and c, a, b, and c. 11 pi over root 3 root 7, that would be the area for this integral. Let's look at another example. How about this one? Minus infinity to infinity, I have a dx divided by 3 plus, we'll say 8x squared. I know here a is equal to 1. That's what it is. B is equal to 3, C is equal to 8. If I were to graph it out, you know the y-intercept is the interplay of what? A and B, A over B. It will be 1 over 3. You graph it out, your y-intercept will be 0, 1 over 3, but it look exactly the same. The area calculation will be a finite value. Based on that template will be your actual answer. The area of the shaded region from minus infinity to infinity will be what? It will be a pi, because a is equal to 1. It's meaningless to write that. Root 3 root 8, but you can simplify 8 root 8. You can just say it will be a pi over 2 root 3 root 2. You can even take it further, pi over 2 root 6. All of these are good ways. They're all acceptable answers, but they'll all be correct. It would represent the end result. We'll do one more quick example, then we'll call it quits for this video. We're looking here at a form which is minus infinity to infinity. I have a 2 dx divided by 4 plus 5x squared. I know here a is equal to 2, b is equal to 4, c is equal to 5. My y-intercept will be 2 over 4. which will be 1 over 2. You want to graph it out, you can. Here it is, 0 comma 1 over 2. You look at a representation such as this, and the area below curve will be a finite value. The finite value is obviously going to be represented by that template. You know that template, a pi over root b root c. Bring the items in. You have a 2 pi over b, which is a root 4, and then a root 5. But you can simplify it. You have a 2 pi over 2 root 5, but you can simplify it. You'll have a pi over root 5. This right here will represent the area below curve from minus infinity to infinity for this function. And with that, we ended this video. Thank you.